Welcome, if you will, David Helfand.
This is a question that has perplexed humanity for its entire history and probably for several hundred millennia before that. What is our place in this vast cosmos? In which chapter of the universe's history do we suddenly appear? You live at a unique moment in the 4.56 billion year history of this planet, in that we can now answer that question with a precision that was unimaginable even 20 years ago. We're there. Well, we're not exactly there because we can't get outside of our galaxy and look at it, but if you were some super intelligence in the universe scanning around for the places where new civilizations were emerging, you'd find one in one of these little flattened disks of stars about 2/3 of the way out. Astronomy is fundamentally different than all the other sciences in that we cannot reach out and touch, control, and manipulate the objects of our study. We can't break off a piece of a neutron star and pour acid on it to see how it responds. We can't go collect an ampule of gas from the atmosphere of a star and bring it back to the laboratory for chemical analysis. We are left to sit here passively, waiting as light, traveling hundreds, thousands, or as you'll see today, even billions of years, in perfectly straight lines through space, just happen to end up landing on one of our telescope mirrors where we can collect the light and analyze it. So everything we know about the universe comes this way, and therefore the study of cosmology, the study of the cosmos, begins with the study of light. Now, for our purposes today, light is a wave. And any wave has two numbers that characterize it. One is the wavelength, the distance between the two peaks of the wave, and the other is the velocity, the speed with which the wave moves along. You can imagine standing on the dock on the beach. You can imagine holding up a ruler and saying, oh, the waves are about 2 meters apart, and you can see how fast they're going by. Now, the wavelength, it turns out, is perceived by you simply as color. Your eye-brain combination measures the wavelength of all the light that's coming to you and sees it as a color. Maybe first I ought to get rid of the cartoon version you have of light. You don't see me standing up here because there's little beams coming out of your eyes scanning around looking for things. You see me standing up here because these devices up here are pouring out electromagnetic waves of energy that bounce off me, scatter in all directions, travel in perfectly straight lines, and the tiny, tiny fraction of them traveling in a perfectly straight line that happen to enter the little black dot in the middle of your eye and are focused by the lens on the retina, communicated by an electrochemical signal to the visual cortex in the back of the brain, and give you the picture of this chubby old guy talking about light. All right? So it's a completely passive activity. You're just receiving this light. And in particular, you perceive my handkerchief here as blue because, well, these devices up here are spitting out all wavelengths of light, long ones and short ones and medium ones. All of them get absorbed by this handkerchief except for the blue ones, which get spit back out, which happen to be short wavelength ones, and so your eye registers those as blue. So wavelength of light just translates directly to color. But you think you have this spectacular, variegated view of the universe. There's these amazing rainbow of colors when the sun is setting over the desert. There's these rich colors ranging from deep reds to purples. In fact, your eyes are pathetic. Your eyes can perceive only a single factor of 2 in wavelength. From about 360 nanometers to about 720 nanometers, just 2. From this size to this size, and that's it. But that's not all that exists. In fact, there are 60 factors of 2, or we call them in music octaves, of radiation that the universe sends us carrying information. And we see 1 out of 60. I mean, imagine how impoverished your view of the universe would be if you only saw 1 out of these 60 lights. You see this spectacular rainbow, but it's a tiny, tiny slice of the entire set of radiation that's impinging on the Earth from the universe and carrying to us the information of what the universe is made of. I mean, your ear hears 10 octaves of music, right? Imagine how impoverished listening to music would be if you could only hear a single octave at a time. Well, in fact, you don't have to imagine that because I've done this. I've taken my favorite piece of music, which is the fourth movement of Beethoven's Ninth Symphony, and I've put filters on the way your eye puts filters on the universe. And here we go. You hear the piccolos and the sopranos, you hear the double basses and the basses singing, you hear the full 10 octaves. Now I'm going to put a filter on so you can just hear one octave the way your eye just sees one octave of the universe. Now you can still sort of tell the music because you can still hear the rhythm. I'm going to change the filter. All right, that's a different filter. Sounds like different music. Not too attractive still. You wouldn't pay a lot of money to go to a concert to hear this. How about this? I'm changing it down another few octaves. Doesn't sound like the greatest piece of music ever written, does it? Because you're so impoverished by hearing one octave at a time. Here's another octave going up another few. Sounds like a bunch of angry crickets, right? You only hear the full music when you put all the octaves together. So that's what's happening when you look out at the universe, or when we use our biggest telescopes made of glass to look out at the universe. We're putting that filter on and seeing just 1/60th of the octaves of radiation that the universe is sending us. So that's wavelength. The other number is the velocity, the speed with which light moves. And it turns out light moves really fast. In fact, nothing moves faster than the speed of light. It moves at 300,000 kilometers per second. That's 8 times around the Earth at the equator in 1 second. But that's not infinitely fast. And so when you see me standing up here on the stage, you don't see me now, you see me a little while ago. Because the light had to bounce off me, and if you're in the back row there, get all the way back to you, which took about 100 nanoseconds. You might say, well, who cares? Because 100 nanoseconds, I don't change very much. In fact, your brain circuits only process speeds at milliseconds, so 1,000,000 times slower. And so in your everyday life, this doesn't make any difference at all. But in fact, when you're looking out, you're always seeing the past. Now, how about when we're looking at astronomical objects? The moon is 384,000 kilometers away. I just told you light travels at 300,000 kilometers per second, so it takes 1 1/3 seconds for the light to get from the moon to you. So when you look up at the sky and see the moon in the sky tonight, you're seeing it as it was 1 1/3 seconds ago. This is not a problem with your eyes, and it's not a problem with your brain, and it's not a problem with our telescopes. It's a fundamental limit of nature that light travels at this finite speed, nothing travels faster than it, and information can only travel through space at that speed. When you're separated in space, you're separated in time. Now, you might say, well, who cares about the moon? 1 1/3 seconds, so the moon doesn't change very much in 1 1/3 seconds. Well, it turns out, contrary to what you see on cable TV, in fact, there was a time that we went to the moon. People actually did this. It wasn't a fake. We went to the moon 50 years ago this summer, as a matter of fact. Neil Armstrong made this one small step for man, one giant leap for mankind, and we saw the astronauts bouncing around on the moon. When that happened in July of 1969, literally half of the people on the planet Earth were watching that on television. It was an epochal event in human history. We had, for the first time, stepped onto another body in the universe. But then NASA did it again, and then they did it again, and then they did it again, and the TV ratings just went into the toilet. I mean, no one was watching this anymore. And they were really upset, and they had a meeting, because NASA, after all, is funded by public funds, and they had this meeting, and they said, what can we do to get people to watch? Now, I know this is going to be tough with this audience, but they came up with a brilliant idea of golf. Now, you know, I'm a physicist from New York. Why anybody plays golf has always escaped me. But why people watch other people play golf on TV has really escaped me. Nonetheless, as you know in this audience, people do that. Millions of people tune in every weekend to watch other people play golf on TV. They said, suppose we play golf on the moon. And there's a huge advantage here because the gravity on the moon is 1/6 of the gravity on the Earth. And as a consequence, you can hit a tee shot a kilometer, like 3/4 of a mile, no problem. Just bang, and it just goes because the gravity doesn't pull it down. So they came up with the idea they were going to send astronauts to the moon with golf clubs. I'm not making this up. They did this. You can find it on YouTube. So the first guy comes down and he sets up the camera so everybody can see the guy come down with the golf clubs on his back. I mean, they've got these bulky moon suits, right? But anyway, so the guy comes down with the golf clubs and he hooks his foot under the cable that connects the camera to the spacecraft. At which point the guy in Houston said, "Look out, you're going to trip on the cable." At which point, of course, the picture went black because it was 1 1/3 seconds ago that he had hooked his foot under the cable. And it took 1 1/3 seconds for the radio signal from Houston to get back to the moon. And 2.5 seconds is more than enough time to rip out the cable. We didn't see the good shots of the guy playing golf on the moon. That's the last time we went to the moon. We've lost the technical capability to do it now. It's all over. All right. And it's all because of the finite speed of light. Now, I think we do what's actually more sensible. We send robots to explore other bodies in our solar system. So we have little robots running around on the surface of Mars, right? And we tell the robot to go somewhere. You say, "Oh, here's a robot. Let's go off and explore that crater over there." Well, Mars, it turns out, is so far away it takes 10 minutes for a light wave to get from Mars to the Earth. So when you see Mars in the sky, you're seeing it as it was 10 minutes ago. And if you're a controller in Pasadena controlling this little spacecraft, you go, "Oh, look, it's getting near the edge of the crater." No, that was 10 minutes ago. Now you've got $1 billion worth of space junk at the foot of the crater. So the way these robots on Mars have to go is the robot says, "May I?" It takes 10 minutes for that to get to Pasadena. The guy looks around with the camera, says, "Yes." It goes 3 meters forward. It stops. It says, "May I?" It takes 10 minutes to get there. The guy goes, "Yes." Takes 10 minutes to get back. It goes 3 meters forward. As a consequence, it takes like 2 months to go a kilometer on the surface of Mars. Because when you're separated in space, you're separated in time. Now, in our solar system, this is a sort of an inconvenience. It's minutes. The spacecraft we sent by Pluto recently takes almost a whole day for the light to get back to Earth, so we didn't know if we'd missed or not for an entire day. But when we get out to the stars, this starts to get serious. Altair, one of the bright stars you can see in the sky, is 20 light years away. That means it takes 20 years for the light to get from there to here. A light year is 10 trillion kilometers, or 6 trillion miles, and it takes 20 light years, 20 years. So when we look at that star, we don't see it as it was today. We see it as it was 20 years ago. And if we were on a planet orbiting that star and had a big telescope and we looked back at Earth, we'd see Earth as it was 20 years ago. Look, no gray, lots more hair, it was really pretty good. And if we were on this star, Arcturus, it's 50 light years away. We look back at Earth, we can literally only see Earth as it was 50 years ago. Look, no beard at all. Note the National Honor Society pin there, it's very important. And if we were on this star here, this Capella's 63 light years away, this is what we'd see if we look back on Earth. Isn't that adorable? My hair is going back to its original platinum color, as you can see. And if we were on this star here, Aldebaran, 65 light years away, you'd see the Michelin tire baby, right? And I have to emphasize, this is not a consequence of a lack of technology. This is a fundamental aspect of space and time. When you're separated in space, you're separated in time because nothing can exceed the speed of light, and light can only bring you information at 300,000 kilometers per second. Now, this is very interesting. Here's a star, which some of you might recognize. It's one of the few constellations I can recognize. Very embarrassing. I didn't grow up building my own telescopes and stuff, so I don't know the names of any of the stars. I know how they work, but I don't know the names. Anyway, this is the constellation of Orion. You see these 3 bright stars in a row, and there's a bluish one. If you're out in the desert, you can see one on the bottom is blue and the one on the top is red. That's because these stars are different temperatures, and therefore they really are different colors. And you can see that if you look carefully in a very dark place. But the one at the top is very interesting because it's 550 light years away, and it's the star we know of in the galaxy that's closest to blowing up at the end of its life. And I'll come back to why that's really important. But when this star blows up, it's going to be 1 billion times brighter. It's going to be a few percent as bright as the full moon concentrated in a single beam of light. It will not be nighttime outside. You'll be able to read a newspaper. Now I say when this star blows up, but of course it could have blown up 500 years ago because we're seeing it as it was 550 years ago. In fact, it could have blown up 549 years, 364 days ago, and when we go outside tonight, this star will be 1 billion times brighter and it won't be night for another year. And we cannot know that because when you're separated in space, you're separated in time. Now, you may think this sounds like, geez, this is a real disaster for astronomers. No, it's wonderful. Because if we want to write the history of the universe, it's all laid out before us. If we want to know what the universe looked like 1 billion years ago, we just got to get a pretty big telescope, look out 1 billion light years, and we see it. It's there. You want to know what it looked like 1.1 billion years ago? You look a little farther, and you see it. It's there. It's like a book. All the pages are there. You just turn to the right page. You want to know what the universe looked like 12 billion years ago? You just need a bigger telescope. We have them. You can do that. You can see objects from 12 billion years ago, and the universe looks very different then. So the entire history of the universe is laid out there for us, and all we have to do to turn to the right page to write this book, because when you're separated in space, you're separated in time. And this is what I looked like 550 years ago. But that's another issue. All right, so doing these observations, we're doing them from this pretty planet Earth. It's blue, and it's green, and it's brown, and it's white. It's really pretty. We like it a lot. It's very comfortable for us. But in the big scheme of things, it's not very impressive. I mean, if you took all the planets in our solar system, all 8 of them, it's like the 5th biggest one. I mean, that's not too impressive. It's the 3rd one from the sun. These other guys are much bigger. These are all to scale in size, but not in distance. If they were to scale in distance, Neptune would be out across the street in the mall over there. But we're all looking out from here. And we look out and we see stars. Now, I'm sure all of you have been out in the desert and you've seen lots and lots of stars. How many stars do you think you can see with your naked eye? 2,000 or 3,000. Someone knew the answer. That's not fair. Usually people say like 1 million, it's a huge. So the answer is 2,000. The darkest place, when you're best dark adapted, you can see about 2,000 stars at any one time. And when you look at those stars, you see they're in different patterns on the sky. They're in particular locations with respect to each other. Some of them are brighter, some of them are dimmer. If you're in a really dark place, you can see some of them are slightly tinted to the blue, some of them are slightly tinted to the red. And if you come back the next night, at roughly the same time, you'll see exactly the same 2,000 stars in exactly the same locations, with exactly the same brightness ratios and exactly the same colors. And if you come back 50 years from now, it's going to be pushing it for some of you, but if you come back 50 years from now, you'll see exactly the same stars in exactly the same places with exactly the same brightness ratios and exactly the same colors. And this gives you a very misleading impression of the universe as this placid, unchanging place. But nothing, in fact, could be further from the truth. Stars are born, they live out their lives, they have a relatively boring middle age, and then they die in a life cycle that's extremely well understood, much better than the life cycle of a human being. You tell me the mass of a star when it's born, I can tell you within 0.1% exactly when it's going to die, which I can't do for myself, which is probably just as well, but whatever. Stars are born in regions like this. Now, I must emphasize, all the pictures I will show you are from ground-based telescopes, or for the most part, satellites in space, the Hubble Space Telescope and other telescopes in other octaves of the electromagnetic spectrum, and they're real pictures. These are not made-up pictures, they're not artist conceptions, they're not colorized. This is what the universe would look like if your eyes were as good as the Hubble Space Telescope and you were above the Earth's atmosphere. So there are regions of space with huge clouds of dust and gas. The gas is illuminated by the stars. The dust is this dark stuff here. Now, you might think the dark stuff is the boring place where there's nothing going on. Quite the opposite. The dust, since it suffuses all of interstellar space, as the gas starts to come together, it gets denser and denser and denser, and it blocks the light from behind. And as a consequence, that's where all the action is. In something like this, you see a huge dark piece of sky. Inside there, hidden from view by all the dust that's been collected by this gas, from you, with your eyes, seeing this single octave of the spectrum, you see nothing. But inside, if we peer in different octaves of the spectrum, we can see there's dozens of stars that are actually in formation. Here's another spectacular example of pillars of this dust-laden gas where new generations of stars are forming. Things like this are about 20 times the size of the solar system. And they're a place where the gas is starting to coalesce. What happens is these big swirling clouds of gas and dust are swirling around like, a puff of smoke. You see eddies and things like that. And randomly, a little extra bit of material coagulates over here. Well, a little extra material means a little extra mass. A little extra mass means a little extra gravity. So the stuff over here and the stuff over there and the stuff over there starts gradually falling in towards this random little clump of mass. But that just makes the clump of mass bigger. So now the stuff down there and the stuff up there and the stuff over there starts falling into that clump of mass. And what happens is the gas clump starts getting bigger and bigger and bigger and bigger, which means its gravity gets stronger and stronger, which means the sphere of influence gets bigger and bigger and bigger, and eventually you have a star in formation. Those little fingers up there, again, are about 10 times the size of the solar system. And you see they're not spherical anymore. And they're not spherical because this gas is turbulent, it's swirling around, and this little piece that started happened to be rotating in one direction. And as stuff falls in, it makes the thing rotate faster and faster. You've all seen this at the Olympics. You know, the figure skaters at the end of their routines, they go into their death spiral, right? They always fling out their arms, and they come in like this, and they spin faster and faster and faster. That's called conservation of angular momentum, and it works here as well. So the gas spins faster and faster and faster, and it collapses down into a pancake, where in the center of the pancake, a star is forming, and a disk of material around that star is where planets can form. So here, in the middle of this diagram, there's a star forming, just of material coming out, and we couldn't study these in detail until we had this remarkable telescope. This telescope consists of 66 antennas, each 12 meters or 40 feet in diameter, on this plane, which is at 17,500 feet in the Andes. It's the largest flat plane at that altitude in the world. So you walk really slowly up there. I've been there. It's really not a lot of oxygen. And we can spread these telescopes out and link them together with optical fibers so they synthesize a telescope that's 18 kilometers in size, 11 miles across. Of course, I would build a telescope 11 miles across because it would collapse under its own weight, but we can simulate that by using these 66 antennas spread out over this plane. And as a result, we can get extremely high-resolution pictures of what's going on in these star formation regions, and this is what we see. We see in the center the star forming, and we see this swirling disk of material around it, and we see these racetracks. Dark regions like here and here and here and there, that's where the planets are coagulating and sweeping up the material as they go around. A solar system in formation. This is the most spectacular one we have. We're looking directly face on at the disk of material, the stars in the center, and this ring right here is exactly the distance of our Earth from our sun. So we see directly these planets in formation. So these stars, formed out of these clouds of gas and dust, eventually are born. Now, what do I mean by born? Well, a star, like the sun, for example, looks like it's this static thing. I mean, the sun comes up every day, and it's the same size every day, and it's the same color every day, and nothing ever changes. And it looks like it's this static thing like the Earth, which also doesn't change size. But in fact, a star is not static at all. It's in this dynamic tension between two fundamental forces of nature. The force of gravity, which is trying to crush the star. Gravity is always attractive, so it's constantly trying to make the star smaller and smaller and smaller. It started out in this huge gas cloud, and it's getting shrunk and shrunk and shrunk and shrunk, but eventually it stops because the core gets hot enough, 15.5 million degrees, and dense enough, about 100 times the density of water, that nuclear reactions can turn on. That the hydrogen gas that makes up 80% of the universe starts fusing together to make helium gas. And that releases an enormous amount of energy. And that energy tries to blow the star apart. So the sun is in this dynamic tension, as are all other stars, where gravity is trying to crush them, and the nuclear reactions are trying to blow it apart. And so indeed the sun does come up exactly the same size every day, because it's in this perfect equilibrium between these two forces. And that's what happens to these stars. They turn on, they blow away their clouds of natal material. Here you see a cluster of stars, maybe 100 stars, and they're blowing away these clouds of gas and dust because they've all now turned on. They've all now turned on and are burning nuclear hydrogen into helium. And we have lots and lots of stars. Lots and lots and lots of stars. This piece of sky is a piece of sky taken with the Hubble Space Telescope. It's equivalent to a dot of ink on your thumbnail held at arm's length. So that's how much of the sky is covered by this picture. And if your eyes were as good as Hubble, that's how many stars you would see. Now, these stars are burning hydrogen to helium. In the case of our sun, for example, it burns 600 million tons of hydrogen to 596 million tons of helium every second. and 4 million tons of matter. 4 million tons of matter is a train full of coal from here to Santa Barbara, okay, disappears from the universe, where's my microphone, each second in the form of energy that keeps the sun shining. All of these stars are in that process. But that process cannot go on forever because the sun is a finite size, and eventually it turns all of the hydrogen in its core, where it's hot enough and dense enough for this reaction to occur, into helium. And there's no more fuel. And so the reaction shuts off. Now, gravity is very patient. Gravity's been waiting for this to happen, in the case of our sun, for 10 billion years, and it will start to crush the star because there's no force opposing it anymore. And it does, crush the core of the star down to 10 times hotter and 10 times denser until the ashes from the first reaction, helium, become the fuel for a new reaction. 3 helium nuclei get fused together to make carbon. Energy starts pouring out of the center of the star again. The star reaches a new dynamic equilibrium at a very different size. In fact, the sun will swell up and gobble up Mercury and Venus and probably close to the Earth as well. And the sun will reach a new equilibrium and burn away until all of its helium has turned into carbon. Now, in the case of the sun, in the case of 98.5% of the stars in the galaxy, that'll be the end of the story. And this is what will happen. Near the very end of their lives, the star will be burning the last little bits of helium into carbon in the core, and the star will start to collapse again because not enough energy is coming out. So a thin layer of material around that core gets hot enough and dense enough to ignite, and that generates more energy, so it puffs the star up again. But then as the star gets puffed up, the pressure is relieved, the temperature goes down, and the reaction shuts off. So the star starts to collapse again, and it goes into this unstable oscillation of collapsing, turning on the reaction, blowing up, turning off the reaction, and puffing off the outer envelopes of the star. Again, these are all real pictures. And here's the outer layers of a star, very much like the sun, being blown off into space. The red represents hydrogen here, the green represents oxygen, and the little star is a little core of the star left behind, only about the size of the Earth, 1% the size of the sun. And here we have another example of stuff being blown off, and my favorite example here where you can see the individual rings, 1, 2, 3, 4, 5, 6, 7. It's been through these pulsations every few 100,000 years, blowing off more and more of its envelope until we're just left with the tiny core of the star. See the little white dot in the center there looks like an eye looking at you. The green is oxygen, the red is hydrogen. These layers have been blown off into space. And that core is now dead. It's dead in the sense that it cannot generate more energy. It can't collapse any further. It's got half the mass of the sun compressed into the size of the Earth, which means 1 teaspoonful of that star would weigh a ton. So picture your SUV collapsed to the size of a sugar cube, all right? But that material is now taken out of circulation and is no longer available to participate in the life of the galaxy because it's this dead little cinder floating through space. It's initially very hot because it was hot in the core of the star, but it gradually just cools off like a log in your fireplace. You know, when it's burning, it's too hot to touch. Just before you go to bed, it's sort of warm to the touch. You get up in the morning and it's cold to the touch. It takes about 10 billion years for a star to cool off that much, but nonetheless, these stars are cooling off. They're called white dwarfs. And the outer layers of the star get puffed off into space and mix with that material that was out there before and help to form new generations of stars. Here's another example of this, and it's an example of what happens when you don't just look with that single octave of radiation your eyes can detect. This is down a couple of octaves, and there's a star in that process, and we looked at this and said, what the hell is going on? The green stuff around there is all water, H2O. And we had no clue until we realized that around our sun, and we think around all stars, there's a halo of about 1 trillion comets. Comets are big, dirty snowballs, so they're mostly made of H2O. And this star puffed off one of its layers and melted all the snowballs. And so this is a huge slosh of water out in space there from these melted comets. Now, if that were the entire story, we wouldn't be here talking about it, because the sun only makes helium, which is sort of useless because it doesn't combine with anything else in the periodic table, and carbon, which is very useful for life, but most of that gets locked away in the core that's taken out of circulation. Fortunately for us, about 1.5% of the stars are formed with at least 10 times the mass of our sun, and they live much more dramatic lives. First of all, they burn their fuel much more profligately. So in fact, they live a shorter time even though they have much more fuel to burn. And they burn hydrogen to helium, and then helium to carbon. But when the star starts to collapse after that phase, the density gets higher and higher, and the temperature gets higher and higher because there's so much overlying material that it can turn carbon, the ashes of the second reaction, into fuel to make nitrogen and oxygen. And then it can go through another step and use nitrogen and oxygen to make neon and magnesium. And then it can go through another step and work its way up the periodic table, building up all of the elements through these cycles of collapse and expansion, the ashes of the first reaction becoming the fuel for the next, until it gets to iron. Now, I'm sure you all remember from your high school chemistry class the periodic table on the wall that iron is number 26 out of the 92 elements. But it just turns out that iron, with 26 protons and 30 neutrons, is the most stable possible arrangement of the protons and neutrons, the subatomic particles that make up the nucleus of an atom. And as a result, when the star, in the last week of its life, 7 of our days, burns an entire solar mass of material from silicon into iron, it then thinks it can just keep going, and it starts to collapse and tries to burn the iron into cobalt and nickel, which are number 27 and number 28 in the periodic table, and that's a disaster. The star, of course, doesn't know nuclear physics, so it doesn't know that 56 is the most stable possible arrangement, and as a consequence, when you try to add more particles, rather than pumping energy into the star and holding it up against collapse, it sucks energy out of the center of the star. And in half a second, something the size of the Earth collapses to something the size of the valley here. That sudden collapse releases 300 times the amount of energy that the sun will produce in its entire 10 billion year lifetime. And a lot of energy at a given place at a given moment is usually called an explosion, and that's what happens. And so we look a few thousand years later, and we see the shards of an entire star blasting out into interstellar space. This is what we see when we look at one that exploded in 1665, only about 3,500 light years from Earth. We see shards of material, and when we analyze it carefully, we see these are moving at 10,000 kilometers a second. That's here to Tokyo in a second. In this direction, they're all expanding outwards. And when we look at the elemental composition, we see it's oxygen and nitrogen and magnesium and carbon and silicon and all the elements of the periodic table that we need. Now, again, this is a visible light picture. If we just expand our imaginations to some of those other octaves that our eyes can't see and move up about a dozen octaves to the X-ray part of the spectrum, this is exactly the same piece of the sky, and you can see every color there represents a different element. This is the synthesis of all the material of which you are made. So apart from the hydrogen in the H2O molecules in your body, every other atom, including the carbon atoms in your thumbnail and the potassium atoms and the calcium atoms in your bones, were cooked up in one of these stars and expelled at enormous speeds into interstellar space, mixed with those clouds of gas and dust where new generations of stars were forming, and ultimately produced a planet that could produce something like you. Here's another example from the southern hemisphere, and another example studied by the astronomer Tycho in 1572, a star that blew up. He saw the star blow up. We look there now in the sky with our X-ray eyes, not optical eyes, we see nothing, with our X-ray eyes, and we see this huge expanding cloud of rich material with all the elements of the periodic table. But that's just stars. And to a cosmologist, stars are sort of boring, They're just local stuff going on. What we want to do is map the cosmos, the universe as a whole, and so we move on to galaxies, collections of stars, collections of order 100 billion stars or so. If we could get outside our Milky Way, which of course we cannot, we believe it would look very much like this. A giant pinwheel of stars. It's rotating counterclockwise. The arms trail off behind, so it's rotating in this direction like this. And we live somewhere like out here. We're not at the center of things. That's New York, that's where I live. This is where you live out here. You live out in the boondocks, quite a ways from the center. About, as a matter of fact, 25,000 light years. So we want to know what was going on in the center of our galaxy. we have to wait another 25,000 years if we want to know what was going on today, or we can look back and see what was going on 25,000 years ago. These galaxies come in many shapes and sizes. Again, I must emphasize these are all true color pictures, and the reddish and yellowish stars are old boring stars like the sun. The blue stars and some of the bright red spotches are newly formed stars. So you can see in this galaxy, this body of the galaxy has a lot of old stars, but the two arms, and there's only two arms in this case that spin out, and again, this one is rotating clockwise, are made up of lots of new young stars that were recently born. Here's an extreme example where the galaxies use up almost all of the gas that it had to make stars. Our galaxy is about 90% of the way there. This galaxy is like 99% of the way there. So in the middle, there's all these old, boring, yellow stars. But at the very, very tip around the edge, the purple, you see there's still a little bit of gas left, and now new generations of stars are being formed out there. Now, we see these galaxies often as in splendid isolation. This is a galaxy that happens to be very close to ours. It's the very closest one, and we're responsible for this mess. This doesn't look like a pretty picture at all, right? But you see there's lots of blue stars and bright red things where new stars are forming. This is a galaxy in which our own galaxy, the Milky Way, is sort of tearing it apart. The disks are very, very, very thin. The action is all in the dark place there, right? The dark place is where those clouds of gas and dust are making new generations of stars. The stars are distributed all over the place, but the stuff is all going on in that thin little disk of material in this big rotating plane. And again, your eyes give you a bias. You see that as dark, black, boring, nothing's going on. And that's because the stars are at a temperature of 5,000 degrees, which is just what your eyes are tuned to, because via evolution they've tuned themselves to be matched to the light that our sun puts out. But this stuff in the dark places there is at like room temperature. It's like 70 degrees Fahrenheit. And your eyes can't see that. If we turn all the lights on here, it'll look dark to you. But if we tune our camera to look at that, this is what we see. The ring is bright, and the stars all disappear. So again, it gives you the richness you can get by capturing all of those octaves of the spectrum, not just the single one at a time. You see these disks of material are very, very thin. That's where the action is taking place. Now, we often see these galaxies as in splendid isolation, but galaxies sometimes get near each other, and this is an example of a big galaxy like ours about to crash into a little galaxy like that. In fact, we've discovered in the last 15 years or so that galaxies mostly grow by cannibalism. They eat little galaxies. And since it will take about 1 billion years for this big galaxy to gobble up this little one, and even we don't make our graduate students wait that long, what we do is put this on a computer and see what happens. And this is what happens. We have a big galaxy and a little galaxy. The little galaxy has gravitational force, so it messes up the big galaxy a little bit, but eventually it's going to lose, and all its stars gets ingested, and this galaxy just eats it up. If we look from the edge, you see the little galaxy can pull stars out of the big galaxy. It can make streamers of material that are flying off in all directions, but the little galaxy is ultimately smaller than the big galaxy. The big galaxy will collect its stars back again, gobble up the stars in the little galaxy, and just be a little bigger than it was before. Now, that's when a little galaxy gets eaten by a big galaxy, but of course, sometimes roughly equal-sized galaxies collide with each other. And what does that look like? Well, here's an example. You see these two a real picture of these two galaxies about to collide. Here's two galaxies even closer together, about to collide with each other. And to image this, we do the same kind of computer simulation. Do equal-sized galaxies. See stars get splashed all over the place. These long tails get spread out. We see those in our galaxy as a result of past mergers, but eventually it all comes together. Here's a weird example of a blue ring of stars and a yellow glob in the middle. You might think, how did this come about? Well, it probably came about with a collision like this, an old galaxy colliding with a young galaxy, going through the center, sending out a wave into that galaxy, and ending up looking very much like that, which is an actual picture of a galaxy from the Hubble Space Telescope, where this kind of collision has occurred. And it's not always, it's important to note that it's not that when two galaxies collide, the stars crash into each other. I mean, if the sun were an orange sitting on my podium here, The Earth would be a grain of sand sitting in the fourth row. Neptune would be a planet out in the parking lot about the size of a pea. And the next star, which is similar in mass and size to the sun, and so it would look very much like another orange, would be in Minneapolis. And there's nothing in between. And so if you throw two oranges at each other from here and Minneapolis, the odds of them hitting each other are really, really small, right? And so when these two galaxies come together, 100 billion stars over here and 100 billion stars over here, the stars just pass right through each other. But the gas, those big clouds of gas, they're big and puffy, and they smack into each other. And when they smack into each other, they generate huge numbers of stars. Our galaxy is forming a couple stars per year. A galaxy collision like this can generate 1,000 stars per year. And they generate so much energy from these exploding stars and things like that they blow material right out of the galaxy. And that's what you're seeing here, the result of a merger that happened some time ago, and the gas getting ejected as a consequence. And there's not only two galaxies that come together. Here's 6 galaxies about to have a real train wreck, right? Their mutual gravity is going to smush them all together. And sometimes you get even richer collection of galaxies like this. Every yellow smudge you see in this image is not a star. It's a galaxy with between 50 billion and half a trillion stars. And there are several hundred of these yellow smudges, from the very big ones in the middle to the little tiny ones like this over here. And they're all swarming around each other because of their mutual gravitation, like bees swarming around a hive, in a tiny region of space, well, tiny to astronomers, 1 million light years across. There's several hundred trillion stars in a region only 1 million light years across. But the most interesting part of this picture is not all the yellow galaxies, although that's pretty interesting, but it's these streaks. Can you see these blue streaks? Like there's one there, two there, there's one up there, there's one up there, there's a big one at the top. Those little blue streaks, you think, well, those must be little galaxies that didn't get eaten yet by these big yellow galaxies. No, it turns out that those are the most distant objects in the universe. They're objects far too faint for our biggest telescopes to see, except for the fact that this massive collection of stars in this small region of space has so warped the fabric of space-time itself, it's turned space-time into a giant telescope that focuses the light from those galaxies and distorts it. They don't actually look like little rings like this, but focuses the light from the galaxies and allows us to see, again directly by turning to the page in the book, what the universe looked like 12 billion years ago. And if we look at a little region of this picture, this little square right here, okay, and we look at visible light, like your eyes can see at the top, you see there's a galaxy here, and there's a little smudge there, and a little smudge there, and there's nothing in the red circle. If we move down an octave, just a factor of 2 in wavelength, we see that galaxy still there, that smudge is still there, that smudge is still there, but now there's something showing up in the circle. And if we move down another couple of octaves, with a different telescope, so it's not quite as high a resolution, we see that smudge is there and that smudge is there, and now there's a bright thing inside the circle. This is direct evidence of the expansion of the universe. What we're seeing is light from these most distant objects have been traveling through space for 12 billion years. And over that 12 billion years, the space, like a rubber balloon, has been stretching. And as those waves of light, up and down and up and down and up and down like this, travel through this expanding space, the crests get spread farther and farther apart. And as a consequence, their light gets shifted from light our eyes can see to light that our eyes can't see anymore at lower octaves in the spectrum. This is the expanding universe. Now, what does this look like? Here's the full moon. Imagine the full moon in the sky. I think it's about that big, about the size of your thumbnail when you held it at arm length. The picture I'm about to show you is the picture I started with. It's a piece of the moon that big. It's that ink dot on your thumb held at arm's length. And this is what happens if you take the Hubble Space Telescope and you put it in space and you stare for a month in one direction. In this picture, there are a few stars. There's a star right there. See the points? There's a star right there. There's another one in here, which I always have trouble finding. Oh, there it is right there. And there's a fourth one somewhere. There's a few stars. Those are stars that are close to us in our galaxy. They're like the foreground of the trees we're looking out through the forest. But every other smudge in this picture, from the big bright ones that look like this when they're red and look like this when they're blue, to the tiniest dots that only in the front row you can see, each of those represents a galaxy with 100 billion to half a trillion stars. And in this tiny patch of sky, the size of an ink dot on your thumb held at arm's length, there are 10,340 galaxies, each with 100 billion stars. But this is obviously a two-dimensional picture. What we'd really like is a three-dimensional picture of what the universe looked like. And because of the expansion of space-time, we can do that. So starting almost 20 years ago, we started a project to measure the distances to each of the little smudges in this picture, so we could make it into a three-dimensional picture. And what I'm going to show you now is an actual fly-through of a three-dimensional picture of what our universe looks like, starting out at Earth and moving out into space. There's our galaxy, the Milky Way. There's the little galaxy that we're ripping apart. And here are a couple of others. You got the sound up? Yeah. You see this little collection of galaxies with us in the middle is really an empty part of space. I put an artificial sphere on here, which is 1 million light years across. And there's nothing around us except those two other little satellite galaxies and us. Well, there comes a couple more. They're a little more than 1 million light years away. But get ready. As we keep pulling back, the 1 million light year sphere is shrinking, right? Smaller and smaller. The screen's now more than 2 million. Oh, but another big galaxy comes into view. The Andromeda galaxy, the other galaxy comparable in size to ours, about 2 million light years from Earth. It's going to collide with us like this. I worked really hard to make the music go with this. This is the largest computer simulation of two galaxies colliding ever done. There's millions of particles in both of them. They're all acting under gravity. And you see they'll swoop by each other in another 2 billion years or so. They'll go by, but they'll come back because their mutual gravitation is so great. They'll fall together. These huge, long tidal tails will be spewed out into space for hundreds of thousands of light years. But eventually, the gravity of these two galaxies is now bigger than before. They pull all the stars back together, and they make one of those big galaxies like the one that sat at the center of the cluster. So let's go back to our picture here. Now we're going to fly out a long way. Again, our galaxy's 100,000 light years across. Those galaxies near us are 50, 100,000 light years away. But we're in a really empty part of space, and you'll see what I mean in a minute when we get to a non-empty part of space. Here's my 1 million light year sphere here. Okay? There's only a few little galaxies plus our home inside there. But as we keep pulling back, remember, there's a couple more galaxies show up. Here they come. They're halfway between sort of us and Andromeda, the big other galaxy in our little local group, as we call it, of galaxies. As we keep pulling back and therefore shrinking the sphere, the screen is now 3 million light years across. Here comes Andromeda. Notice it has galaxies it is gobbling up to, that one, and that one's about to fall in as well. So it's also growing with time before it collides with us. There's a couple more galaxies, but then we keep pulling back. The screen's now 10 million light years across. There's no other galaxies. We're in a really empty part of space. Oh, there's one over here. And there's one down there. There's one down there. See that one down there? The sphere continues to shrink as we keep pulling back. This is the real three-dimensional distribution. We spent a lot of time on this. This is not a movie. This is a real, well, it's a movie obviously, but it's a real three-dimensional disposition of where these galaxies, here comes some more, and oh, there's a whole bunch of them up there. Wow, look at them all. That's still 1 million light years across, but now we see there are regions where there are hundreds of galaxies within 1 million light years, like that big yellow one I showed you. And we keep pulling back. We see tens of thousands, hundreds of thousands. There's about 2 million galaxies in this picture from which we've measured the three-dimensional locations in space. And I'm going to spin it around for you and show you a sphere that's 1 billion light years across, 1,000 times what I showed you before. And you see there are regions of space that are quite empty, like near us, and there are regions that are very dense with galaxies. Now, I haven't put all the galaxies on here, because this whole screen would be white if I did, so they're not actually in these sheets like this, but I put, see, not in those planes, I've just put those on so you can see them. And as we continue to pull back, we get fainter and fainter and fainter galaxies. We're right at the center here. Now, it looks like there's more galaxies around us, but that's just because they're easier to see close to us and harder to see far away. But you can see we're mapping the universe out to several billion light years in space. And as we continue to pull back, we get to the point where our telescopes can no longer measure the speed with which these galaxies are receding from us, and therefore the distance to them. The galaxies just peter out, and we can't see them anymore, although we have no reason to expect that the universe looks any different out there. But oh, something new is coming into picture here, something blue and yellow and red. What is this? It covers the entire sky. You look in that direction, that direction, that direction, that direction. There's this glow of the entire sky. And as it starts to come into view, you can see what a small piece of the universe we've actually managed to map in the white dots, whereas the entire sphere represents the 13.8 billion light year radius of the universe out to which we can, in principle, see. And what is that? That's radiation that comes from all directions. And in fact, it's unbelievably smooth. It's incredibly uniform. I've made it look mottled here with dark blue places and bright red places, but in fact, it's amazingly smooth. If I look in that direction or that direction or that direction or that direction or that direction, it's the same to 1 part in 100,000. And to picture that, I have a New York analogy. It's the Empire State Building, and the Empire State Building with an ant standing on top of the antenna. That's the biggest fluctuation you see. So I've blown up these fluctuations by a factor of 1,000,000, so you can see the ants. And the blue places are the dense, cool places in the universe, and the red places are the hot, less dense places in the universe. Now remember, when we look out into space, we look back into time. So we've turned the history all the way back to when the universe was only 380,000 years old. It's 13.8 billion years old now. 380,000 years is the blink of an eye. And in fact, this is the distribution of matter and temperature at that time. And what we can do is follow forward one of these blue regions and find one of those dense clusters that we saw in the yellow picture before, or one of these red regions, and we find a region around our Milky Way with very, very few galaxies in 1,000,000 light years across. The sky looks like this all the way around, and it allows us a baby picture of the universe when the universe was only 380,000 years old. That's what we know about the universe. Wait. That's what we don't know. This is great news for astronomers. Talk about job security. Everything I told you fits in that 4% wedge. Everything I told you about the gas and the dust and the stars and the galaxies and the light and the microwave background all fits in that 4% wedge. We know there's another 28% that consists of something we cannot see at all. We've noticed this since the 1930s. We're still clueless about what it is, but we know it has gravity because it exerts gravitational attraction of things, and so we call it dark matter. And then, to outdo our cluelessness, we know that 68% of the universe is made up of something we're even more clueless about called dark energy, which rather than allowing the universe and its gravity to slow in its expansion, is actually accelerating the expansion as the space gets bigger and bigger. Now, we don't know what dark matter is, and we don't know what dark energy is, but we can measure their properties with exquisite precision. And as a consequence, we can make a simulation of the entire universe. We can make a simulation where we put millions of particles in a computer, arrayed almost perfectly uniformly with those tiny fluctuations that you saw in the map of the background. And we can run the computer simulation forward in time, and we see what happens, that this uniform universe becomes a lumpy universe with big regions of empty space like where our galaxies live and big clusters of galaxies like we've seen before. We go from a nearly uniform universe, which we see when we turn to the last page of the book, to a universe, as we map forward in time, flipping through the pages, that comes to look like the universe that we see today. Now, there's a big number that I've used several times in this talk, and that's 100 billion. 100 billion is the number of stars in a galaxy, typical like ours, and there's about 100 billion galaxies in the visible universe. 100 billion is a number hard to imagine, so I got a good analogy for you. Take a New York City block between 2 avenues and 2 streets, and you build a warehouse that's about 15 feet tall or so on that, and you fill it with marbles this big. That's 100 billion. Okay. So there's that many stars in a galaxy, and there's that many galaxies in the universe. It turns out there's also about 100 billion atoms in each of the cells of your body. And it turns out there's about 100 billion neurons, each of which contains 100 billion atoms, in each of your brains. Now, the fact that these 4 radically different numbers are all 100 billion is a complete coincidence. But the fact that this 100 billion neurons can apprehend it all is what makes science wonderful. Thank you very much.